Hello, everyone. My name is Shahrzad, and I'm currently a research fellow at Northumbria University, and I'm very glad to be able to show you our results. My presentation today is about integrated sensing and actuation capabilities of flexible surface acoustic wave devices that are composed of metallic and polymer layers. Our objective is to develop an integrated platform that is capable of both sensing and actuation using a single geometry. And one way of doing so is using surface acoustic wave devices. These devices are composed of metallic interdigital fingers that are fabricated on a piezoelectric substrate, which are capable of detecting and also generating surface acoustic waves. So when power is applied to the electrodes of the device, acoustic waves are generated and will travel along the surface. So if a droplet is placed in front of the IDTs, the wave will leak inside the droplet, and this can lead to different phenomena such as streaming, pumping, jetting, or nebulization. In this slide, I have put streaming and pumping as examples. For example, in the middle, you can see the streaming of the polystyrene particles. So when the power is above a certain level, the streaming will happen, and afterwards, by increasing the power furthermore, it can lead to pumping, and further increasing power will lead to pumping with higher velocities and eventually will result in jetting or nebulization of a droplet. Acoustic wave devices are also capable of sensing. So these devices have resonant frequencies, and there are different elements that can affect the resonant frequencies of these devices. These elements can be mass, conductivity, temperature, pressure, dielectric constant, and so on. So when these parameters around the device change, it will cause a change in the resonant frequency as well. And by detecting that change, sensing can happen. Our proposed device have interdigital fingers that are patterned on a zinc oxide substrate as a piezoelectric layer, which is deposited on a tri-metal layer of nickel, copper, nickel, and it is bonded to a PET substrate. We have characterized the devices that have various wavelengths, such as 64, 100, and 160 micrometers. And for characterization, we have monitored the reflection coefficient, and the frequency of these devices will depend on two elements. One is the speed of the wave inside the substrate, and the other would be the wavelength of the interdigital transducer. So by increasing the wavelength, the frequency will shift towards a lower frequency. We have used the fabricated devices to monitor the responses to temperature change, and also when they're exposed to UV light. On the left-hand side, you can see the temperature coefficient of frequency measurements, which means that we monitor the change in frequency with respect to a reference frequency when the temperature was changing. So this can be crucial when maintaining a constant temperature is very important for the operation of the device. And we could observe that the devices that had higher wavelengths when they were calibrated at their lower frequency mode showed a more significant result to the temperature change. Also, we monitor the response of the device when they were exposed to high intensity of UV light. In this case as well, we observed that the devices with higher wavelengths showed a more significant response towards the UV intensity. We picked the device with the wavelength of 160 micrometer and put a SSI droplet of 1 microliter in front of the IDTs and apply power to the electrodes. We could observe that pumping is achievable when the power is around 1.8 watts. And afterwards, by changing the power, the velocity of the droplet will change. So increasing the power up to the point of 3.5 watt will increase the pumping velocity, and afterwards it can decrease the velocity. And the reason for this phenomenon is because that by substantially increasing the power, some of the power will be converted to heat and will be dissipated inside the polymer substrate, and then it's lost. That's why the velocity of the droplet will be lower. As conclusion, in this paper, we have reported a flexible surface acoustic wave device that can be used as an integrated platform for sensing and actuation purposes. And we have tested the response of the device to the temperature variance and also UV intensities. And we finally investigated the actuation capability of our proposed device by pumping a sessile droplet. Our results indicate that these structures have the potential to be effectively integrated into the next generation of point-of-care devices. That's the end of my presentation. Thank you for watching this video, and I hope to see you in the conference.